he's very busy, but we are very lucky that he could make room in his agenda to come here. Without much delay, I let Petar speak.
Thank you, Victor. Good afternoon, everyone. Yes, I am professor at Stony Brook University. I don't know how many of you know where it is. It's a small town which is on Long Island, and Long Island is just extending eastward from Manhattan. So when you go to New York has 5 boroughs. One is Manhattan, and the other two more are on Long Island. One is Queens, and the other one is Brooklyn. When you land from Europe, you usually go to JFK. JFK is on Long Island. So when you look at Long Island, so Stony Brook is somewhere in the middle on the North Shore facing Connecticut. And so it's sitting on Long Island Sound. And it's one of the 64 actually campuses of State University of New York. And the 2 largest are Stony Brook and Buffalo. And they are considered to be the flagships of, according to the governor of New York, of the SUNY system. So yes, as Victor said, I fell in love with particle filtering when I actually had my first sabbatical, and it was in Cambridge many years ago. And when there was no internet, and I learned about particle filtering from the people who actually reinvented it. And from then on, I was hooked up. And then I had some colleagues who visited. Among them was Victor and some others. The advisor of Dennis, Joaquin Miguez, who will come later in the week. And I was kind of, without being proselytizer, I think proselytizing, trying to convince people this is a nice and good area to do research on. And these days, I always go back to particle filtering. I work on maybe some other problems, and but they all have to do with particle filtering some way, one way or the other. And before I start, I would like to first make an acknowledgement from what I will present today. These are 2 former students who have worked with me on what I will present today, especially the last part of the presentation. One is Yu Hao Liu, who is, so they're former students who graduated last year. Yu Hao is today working for Capital One in Washington, D.C., and Marzia Djuric is at Cornell University. So, and of course, this work was also supported by the National Science Foundation under this award. So my lecture will be split in 3 modules. The first one will be on the basics of Bayesian filtering. Then I will talk about Gaussian and deep Gaussian processes, which will be the prerequisites for the last part on deep Gaussian process or deep state space models. So it was great that Dennis had this presentation this morning, because I will build on what he was talking about today. Maybe I will repeat some things, but it's always good to repeat things. At least you hear from me the same things, but from slightly different perspective. And then during the break, I actually was chatting with ChatGPT to see what ChatGPT will tell me about Bayesian filtering. So let me read the conversation. So I asked, what is Bayesian filtering? And the answer was, Bayesian filtering is a statistical technique used for classifying data based on probabilities. It is commonly applied in spam filters for email, where it calculates the probability that an incoming message is spam or not spam based on the presence of certain keywords or patterns. Then I wanted to dig in a little more and said, is it used in tracking processes? And the answer was yes, Bayesian filtering can be used in tracking processes as well. For instance, it can be employed in tracking systems to classify and predict the movement of behavior of objects based on observed data and historical patterns. And I asked one more time, what about tracking targets? Yes, Bayesian filtering is often used in tracking targets, such as in radar systems or surveillance applications. It helps in predicting the position, velocity, and other characteristics of a target based on sensor data and past observations. By the way, this was a big area that I was involved in when I started to work on Bayesian filtering. And then I didn't want to give up. What about medicine? Yes, Bayesian filtering is also used in for various purposes, such as disease diagnosis, patient monitoring, and treatment optimization. It helps in analyzing patient data to make predictions about disease progression, treatment outcomes, and the likelihood of certain medical events. In fact, these days, this is one of the major areas that I work on, how to apply Bayesian filtering to in medicine. And I'll elaborate a little more on this as we go. And then I asked, what about neuroscience? Yes, Bayesian filtering is utilized for tasks such as analyzing neural activity, decoding brain signals, and modeling neural processes. It helps in interpreting complex data from experiments or brain imaging techniques to understand how the brain works and how information is processed within neural networks. And the last question was, and finance? Absolutely. Widely used in finance, but that's such as risk assessment, portfolio management, fraud detection, and algorithmic trading. It helps in making predictions about market trends, identifying patterns in financial data, and making informed decisions based on probabilities and historical data. So the reason I read this is because I'm sure you were all, this is why you're here after all, you're convinced that Bayesian filtering is indeed a great area for doing research, and there are so many challenges in doing Bayesian filtering. And one of them actually is something that was alluded to earlier today, this high dimensional data. So I'll give you one interesting example why, especially when you do things like particle filtering or Monte Carlo or something, this curse of dimensionality. I asked Victor if he would speak about this more. He said a little bit. Try to extend it, Victor. So, I'll give you one interesting example. Suppose you all know from basic probability theory, if you want to draw a point lies within an interval of 0.2, and you're drawing uniformly from 0 to 1, the probability that you'll get a point where you want is 0.2. And then if you now use a square with sides 1, and then you want on each side to have a point within particular 0.2 interval, then the probability goes down to 0.04. So now imagine that you have a hypercube of dimension 48. It's not that big dimension. So hypercube of dimension 48, where each side of the cube is 1. And then you describe a hypersphere inside that cube. So you have a hypercube of dimension 48, and then inside that cube you have a sphere, hypersphere. And now you are drawing randomly, uniformly from the hypercube, and you want to get a point inside the hypersphere. It's a very simple experiment, and you do it with a computer that can generate 1 million draws per second. 1 million draws per second. And you want to know what is the expected time to get the first sample within that hypercube. This is not complicated math. If my calculation is correct, if we start drawing samples at the moment of the Big Bang, we'll still be waiting for that first sample to get in that hypercube. This is how challenging it is to, if you do it without some clever tricks. So of course, drawing uniformly is not the cleverest way of finding that point inside the hypercube, but this is how challenging high dimensions can be. All right, so let me get back to now my lecture. So we are here to talk about stochastic filtering, and typically, at least when we have stochastic filtering, we deal with two types of processes. One is the observation process, and the other one is a hidden process. So today, Dennis was talking about observations when he was showing examples of tracking targets. So the observations represent typically sensor measurements. And then the hidden process is something that is intrinsic for the target, which may be the location of the target and its velocity, its acceleration, and other physical parameters. So we have two processes, the observed process and the hidden or latent process. So what I would like to emphasize in this talk is that these processes can be or are usually vector processes. A good example is from neuroscience. In neuroscience, you have multivariate time series. These are signals measured simultaneously at the same time. When you have EEG data, you can have 64 such time series that have to be processed at the same time. And then you have something that is now a hidden process, and that this hidden process is supposed to mean, it's hypothesized to represent something that relates to the state of the brain. So both are can be high dimensional. So you have a multivariate observation process and also multivariate hidden process. So typically what the objective is to learn something about these latent processes or to estimate them based on the observation processes. So there are a couple of ways to go about this. One is, and this is something that was explained earlier today, where we assume models about the processes. So what we have is, and I will elaborate this more as we go, here is the objective. So what we have to do is to make inference about the hidden, the latent processes in some meaningful way. And what is beautiful about the Bayesian approach is that it not only provides point estimates, in fact, it provides first distributions from which one can obtain any type of point estimates one wants. So all the information is in the posterior distributions. So what I will do in my presentation, this is also, these slides also slowly introduce the notation. I'll use boldface to denote vectors. And then the dimension of xt, which is going to be the latent process, the hidden process, is dx, and the observation process will have dimension dy, yt, and t is a discrete time index. And dx and dy are the dimensions. So what is also nice about Bayesian filtering, the sampling of these processes does not have to be uniform. So one can have any time instances at which you sample yt, and then for these samples you can estimate the hidden process. So one assumption that was also mentioned earlier is the Markovian assumption about the hidden process, and this is given by this first equation. So there you can see that when xt is conditioned on the previous sample, so the latent process, what is enough is to know just the previous sample. So at time t, one only needs to know x of t minus 1. Now, of course, when you analyze data, you have to start at some point, and this first point, x0 here, is having a prior distribution p of x0. And then from then on, things start to evolve in a very natural way, very harmonious way, I would say, using Bayes theory. So here is one example. This is now an example with scalars. So you have again, I'm sorry, maybe for some of you who are very advanced, you see some basic things here, but hopefully with, as we progress, things will warm up a little more, and then you'll hopefully learn something new. So here we have xt, which is a simple autoregressive process with first order, and then where a is the parameter of the model, and ut here represents stands for independent random samples. And then one can see simply from this equation then how one can write this equation that p of xt conditioned to know the previous samples actually become p of xt given xt minus 1. Here we assume that a is known. It's interesting though that if a is not known, this is not going to be true anymore. So only if a is known, you can write this Markovian assumption. Yes, so to write p of xt, given all the previous samples, one only needs to know xt minus 1. So here is again the same schematic diagram that you saw earlier. So this is the generic form of state space model. SSM states for state space model. So we have some initial x0, and then it moves on and X1 is produced using some probabilistic machinery. And then one obtains observations given X1. This is this arrow that goes from X1 to Y1. And then X1 becomes X2 at time instant 2, and then X2 produces observations Y2, and so on. So in this case, we have only T observations, capital T observations. So there are actually several ways of describing this model. One is to simply work with probability density functions. So P of X0 is the prior that is generating the first vector X0. And then we have transitional PDFs, P of Xt given Xt minus 1. And P of Yt given Xt is a conditional PDF of the observations Yt given the state Xt. Now, of course, from our estimation point of view, when Xt is not known, P of and Yt is observed, P of Yt given Xt is our likelihood. So I will get back to this vector notation in the following modules. So the rest of this module will be using scalar processes Xt and Yt. So what are the tasks that one has to deal with in Bayesian filtering? So the first one is simply to get the filtering PDF. So as you can see, it is P of Xt given all the measurements from time instant 1 to time instant t. So this is what is happening now. What is our state Xt? So when we had this example of target tracking, we would like to know what is the current location of the target, and what are the components of its velocity. So that is the filtering PDF. Smoothing is something that one can do when one goes back, does not only want to know what is the state, the hidden state at time instant t, but you go back in time and you try to find the density of Xt minus tau, where tau is greater than 0, given all the measurements from 1 to t. So that is a smoothing operation. There are now two predictive PDFs that are of interest. One is the predictive PDF of the state. So now you want to find the state tau instance from now, Xt plus tau, given all the measurements from time instant 1 to time instant t. And then finally, the predictive PDF of the observation Yt plus tau, given all the measurements at Y1 from time instant 1 to time instant t. Now, one thing that is very important to note here is that when we do Bayesian filtering in the real world, you will never know your latent process. The only thing you know is your observations. And the way how you can judge whether you're doing well or not is using these predictive distributions of the observations. You never know what Xt is unless you have a controlled experiment and like with robots and you know where they are. But when you do, for instance, real target tracking, unless you go there and take pictures of the target, you will not know where the target is or any other problem. For example, in finance, Denise mentioned the stochastic volatility model, and I'll mention it later. You will not really know exactly what it is. It's only an estimate. So the only real thing that is that we can undeniably say is known to us are the observations. So some examples. When we do Bayesian filtering, and the title of this lecture is Sequential, we want to do it sequentially. What that means is that when you want to estimate the filtering PDF, X of t, given all the measurements from 1 to t, you would like to do it just by using the previous filtering PDF. the PDF of xt minus 1 given y1 to t minus 1. Similarly, for the smoothing PDF, you would like to find the PDF of xt minus tau given y1 to t, but you want to find it from the smoothing PDF of the sample that came after. So it's interesting now that in filtering, finding the filtering PDFs, you go from left to right, where left means earlier time, right means time later. Now you go actually backwards in time. And so you find the smoothing PDF of at time instant t minus tau by taking the smoothing PDF from the time instant that came after. Now, obviously, in estimating the predicted PDF of the latent state, you go again forwards in time, and you find this predicted PDF by using the predicted PDF of the previous latent state, and so is the case with the PDF of the observations. So the PDF of yt plus tau is obtained from the PDF of yt plus tau minus 1. Now we also can have this problem where we want to know the complete trajectory of the latent state, and again it was this problem was also discussed earlier today. So again, in summary, this is what I was saying so far. So in Metherm, we have for filtering this transformation, so to speak. You go from the filtering PDF of xt minus 1 to the filtering PDF of xt. In smoothing, we go backwards from xt minus tau plus 1 to xt minus tau. Then for the prediction, we go forwards again in time, xt plus tau minus 1 to xt plus tau, and prediction again, but of observations, yt plus tau minus 1 to yt plus tau. So here is the example that was mentioned earlier today, but in math terms. So suppose that one has a process yt that represents, for example, log returns of a particular asset. So this is an example for finance. And then the asset log return over the period t minus t to t is defined by this equation, where ct is the price of the asset at time t. Then the log return depends on the unobserved volatility of the asset at time t, and the model for that is given by this equation. So yt is modeled, given xt, is modeled as a Gaussian with mean 0 and variance e to the xt. So xt is not observed. The only thing you observe is your asset prices. And then one can use this model to, in fact, do predictions of yt given the previous observations of the asset. So in this case, the stochastic volatility represents the state process. So earlier today, you saw an example of target tracking, where target has 4 processes of interest: the location, 2 dimensions. It's in 2-dimensional space. If you're flying drones, it has to be 3-dimensional. And then the unknowns here is only 1-dimensional. xt is something that one needs to track. This is the hidden process. So, for example, if you further assume that this process xt is a Markov process, for instance, like an authorization that I mentioned earlier today, then one can write this process xt. One can represent the PDF of xt given only xt minus 1, given this equation. So it's a Gaussian with mean mu x plus some parameter a, then that multiplies xt minus 1 minus mu x plus sigma x squared. And then one can finally define also the prior of x0 p of x0 given by this Gaussian. So one thing that we will see in my other modules is also the problem where some of these parameters that are shown here, A and sigma x squared, are not known. So that's what reality is. One has to estimate them as well. So I like to use the word unknown. So unknowns can be processes, unknowns can be parameters, unknowns can be models. This was earlier alluded to model selection. So it is also an unknown because, as you know, these are only models and one has to choose either one of those or use all of them at the same time and use the information that they provide. So in this particular example, all these parameters, A and sigma x squared and mu x, are known, assumed to be known. One thing that we often like to do in Bayesian filtering and in general in Bayesian machine learning is to work with generative models. So we know how the data are generated. And then what we do with filtering or estimation, we do the opposite. We infer all the unknowns. So all the unknowns, again, can be the hidden process or all these other parameters that are used in the model. So the generative model in the case that I just had on the previous slide is that x0 is first generated from the prior. Once x0 is known, then one can proceed recursively in time, from time instant 1, 2, and so on, by using these two steps. First, you generate your hidden process, and then you generate your observation. So I mentioned earlier that in real life, you never know xt, you never know your latent process. However, when you do simulations, you know everything. And this is where you first want to make sure that all your algorithms work well, so that at least you know that they work well. If they don't work in the real world, it means that your models are not good. It's not the algorithm. And this is just a nice example how actually this, at least for the example of stochastic log volatility, how these signals may look like. On the left, you see the log volatility, and on the right, you see the log recurrence. So there is a second formulation of what I just spoke about. So the first formulation was given by probability density functions. The other formulation is to work with something that you see now on the screen. So the hidden process xt is considered to be some function of the previous value of the hidden process, xt minus 1, and then some perturbation ut. And the same thing for yt. So it's some function h that is a function of two arguments. One is the hidden process at time instant t, and some other perturbation vt. And then these ut and pt variables are other random processes. Typically, they are assumed to be independent. But I have also personally worked when they are dependent. That this is not so uncommon, for example, in finance. And G and H, the functions are assumed to be known. This is very important, are assumed to be known. You know the functions, but you don't know xt in this case. And you, of course, don't observe qt and vt. So just as a prelude, what you will hear, especially in module 3, is I will talk about ways how to go about estimating xt when you don't know g and you don't know h. So too many unknowns, but there are ways how to go around this. So what we will do is we will try to employ some, let's call, modern machine learning methods. As you know, machine learning methods are primarily known for estimating functions rather than parameters. And so this is going to be the main part of what we will do as we proceed. So obviously, these two representations or formulations are equivalent. The first one with PDFs and the second one just by using these equations. Once you know the PDF of ut and vt and you know the functions g and h, you can represent these two equations using PDFs. So they're just equivalent formulations. So this is now the example that I showed with stochastic volatility. What we had before was representation using PDFs, and this is a representation using functions. So now xt is a function of xt minus 1, like what you see in the first equation, and yt is a function of xt using the second equation, and where ut and vt follow these distributions. They're both Gaussian. So now I will switch to a little bit more complicated problems, in the sense that so far we only had a latent process and observation process. But now we'll add to the mix other unknowns, and these are the parameters of the models. These are typically assumed to be static parameters, which means parameters that do not change with time. So they can appear in the state equation, and they can appear in the observation equation. And in general, these parameters have their own dimensions. Theta g would be the parameters that go with the observation equation, and theta h would be the parameters that go with the observation equation. Now the problem actually becomes a little more complicated, in the sense that now we have to find the joint PDF of xt minus, how to actually convert the joint PDF of xt minus 1, theta g, theta h, given all the previous observations, to an updated posterior, joint posterior xt, theta g, and theta h, given all the observations. So this is the filtering problem. So this is like the baggage you get when you don't know the parameters. And then the same thing for smoothing operation, and then the prediction of the state and the predictive PDF of the observation. So the predictive PDF of the observations, you have the joint PDF of yt plus tau minus 1, theta g, theta h, given y1 to t, and then you have to convert this again using what you know at time instant t minus 1 to an updated posterior of the observation of the predictive density of yt plus tau, theta g, and theta h, given all the observations from time instant 1 to time instant t. And then here's what happens with the stochastic volatility example. So there we have the equation for xt, but now the parameters ux, a, alpha, beta, they are not known. And I'm sure that this will mentioned by someone later in the summer school, how to handle these static parameters, especially in the context of particle filtering. Static parameters are not very friendly to particle filtering, and one has to do something about that. And there are various ways of doing it, but particle filtering likes something that changes all the time. And but it's important to mention at this point that life is a bit more challenging, in the sense that besides the hidden processes, we also have to deal with unknown but fixed parameters. And these unknown and fixed parameters can appear both in the state equation and the observation equation. And the last thing that I would like to mention today, because later in the module. So I wasn't sure what it is we'll talk about. He did mention Kalman filtering, so I will also mention it, and I'll more or less repeat what he said. So when we deal with state estimation, one particular model that is having an exact solution is this one that you see on the screen. So here yt is a vector, and it is a function of another vector, which is the state vector xt. Xt is multiplied by some matrix B, and then vt is observation noise. All these vectors and matrices are conformal, so they are with the right dimensions. xt is the latent process. A is a matrix that multiplies xt minus 1, and then ut is another perturbation. And now ut and vt are Gaussian, and with mean 0, and they should be in boldface ru and rv. These are the covariance matrices. And what is important to pay attention to here is that all these parameters, meaning matrices, Ru of the noise and Rv are assumed to be known. And A and B, also important, they are assumed to be known. So there's a lot of strong assumptions here. You know A and B, you know that U and V are zero mean, and you know the covariances of U, T, and T, and they're denoted here as RU and RV, and they are all known. So then, in order to get the optimal solution, one has to implement these equations. First, what one does is you predict the next state from the estimated state time instant t minus 1. And as you can see, this estimate is simply saying that you take the previous estimate and propagate it to get xt tilde. So this is because the noise is zero mean, and this is the best guess of your estimated time instant t. Then what you also have to do is to find the covariance matrix of xt tilde, which is given by that second equation. So this is the prediction step. And then you have the update step, which which involves the computation of kt, which is a matrix known as Kalman gain. And as you can see, it's a function of this predicted covariance matrix and the matrix B. Then you have, now once you have kt, you update this x tilde t to your estimate of xt tilde. And then finally, you have to find the covariance matrix of xt tilde. So what you can notice here is that xt hat is actually composed of two terms. The first term is your predicted value of xt without seeing yt. But then once you see yt, you correct for this estimate. And in the correction, use the Kalman gain. And what you also use is this error, the error between what you predicted, yt tilde, yt. What you predict is this product here, b x tilde t. So this is your predicted yt. So yt minus yt hat, let's call it. So as you can see, the Kalman filter only learns if there is a mistake. If there is no mistake, xt tilde will not be changed. And then sigma t hat is, as I said, the covariance matrix of xt hat. So one interesting thing that I would like to mention here is that, and something that you should not forget, this actually filter is also optimal when you don't assume anything about the PDFs of the process Cs. In other words, what we did here was to assume that UT is Gaussian and then VT is Gaussian. This is also optimal filter in the least square sense if you simply assume that these noises UT and VT are a zero mean, and with covariance matrices RU and RV. You don't have to assume that they're Gaussian. In fact, I remember I attended a lecture by Professor Kalman about 20 years ago, where he was suggesting don't use Gaussian assumptions. Of course, many people in the audience disagreed with that, but that's what he wanted. So he felt that using Gaussian assumptions is too much. So, but the point though is that to use these equations, you're also having an optimal solution from a least squares point of view. You don't assume anything about the distributions. So here is just one brief example of just to get a feel how this filter works. Again, I go back to scalar case where YT is an observation where the hidden process is multiplied by some constant B. And then, so B is known. And XT is an autoregressive process with parameter 0.8. Sigma U squared and sigma V squared has some values. And then just to see how actually this filter can work well, it's given by this plot. So the state is drawn here in red, and the Kalman filter estimate is in black. What is observed is given in blue. So, and of course, those of you who have tried this, I'm sure you have been assured that that this filter can work well. Obviously, how well it works depends on the noises you have in your data. For instance, here you have V of t, which is the observation noise with pretty large variance. So here one could argue the signal to noise ratio is not very high. So obviously the performance would depend on what kind of in the real world, what quality of data you have for tracking. So this will conclude my module 1. Maybe I should have said this in the beginning. You can interrupt me at any time with questions. So let's state. So do you have any questions for me at this point? I would take this that what I said was clear. So good, thanks. So let us move on. All right, so this module is on Gaussian and deep Gaussian processes. Let me ask a question. How many of you are familiar with Gaussian processes as they are applied to machine learning? All right, so it's pretty good size. That's nice. So I hope you'll not find what I will say more. So first, just a reminder, because we talk about Gaussian processes, when you talk about Gaussian random variables, we want to, at least I want to talk in more detail about Gaussian random variables. So here is obviously you're all advanced and advanced on this, but typically, of course, we want to say that Gaussian random variables have a PDFs that are defined by two parameters. These are scalars, so the mean and the variance. And this is an example with a couple of Gaussians with different means and different variances. This is a PDF of the Gaussian. So, but what will be important in what we will do is to work with multivariate Gaussian PDFs. And again, they are defined by a mean vector mu and covariance matrix sigma. And here the dimension of x is dx and sigma is the covariance matrix that is positive matrix. And just a couple of examples. So on the left, you see one such Gaussian that is centered at 0 and with this covariance matrix. On the right, you see a contour plot of this Gaussian. So this Gaussian is with variables that are correlated. And this is another Gaussian with different means and different correlations between the two variables. Now, what is also important is to mention one beautiful property of the Gaussian vectors. So if we have two random variables, so bivalent Gaussian with two random variables, x1 and x2, so the conditional PDFs of in this case, x2 given x1 is also Gaussian. And this is something that will play an important role as we go on. And then the conditional mean is given by these equations that you're all familiar, I'm very sure about. And then the natural extension of multivariate Gaussians is Gaussian processes. So again, reviewing basic tools of the theory, you know that random processes are infinite collections of random variables, and they're indexed by indices from some mathematical set, and typically in at least in most of the time this set is time. It could be also space, or it could be both space and time, or some other variable. So now what is important is that if we have a stochastic process that we call Gaussian, then if we take samples from this process, any collection of samples from this process is having a multivariate Gaussian distribution. So so that is important to keep in mind. So then consider a discrete time Gaussian process, x1, x2, and then, as I said, any subset from the process has a joint PDF that is multivariate Gaussian. And if this, so for example, if you take just one sample, different at time instant, whatever call it T1, then the PDF of that random variable will be Gaussian. At time instant T2, we define this random variable x2, it will be also Gaussian. The joint PDFs will also be Gaussian, and so on. So now, what is also important to mention here is that the distribution of a Gaussian process is the joint distribution of its infinitely many random variables. And what it means is it is a distribution over functions with a continuous domain. So what I mentioned earlier was, what I said was, we will work with problems where we do not want to assume the functions that describe how a state process changes over time, or how a state process is mapping its value to observation. So we will have to deal with unknown functions. So what we would like to do is to treat these functions as random entities. And then if we treat them as random entities, then it means that we have to choose a prior for these random entities. And the prior for us will be the Gaussian process. From then on, we just follow what you know about Bayesian theory. Again, I repeat, we will use Gaussian processes to be our priors of the functions that are unknown to us. Then with these priors, once you observe data, you will update your priors to posteriors, and you will change, of course, what you know about the functions that are used in your model. And we have two places where we will do it. One is in the observation equation, and the other one in the state equation. And then, as I will introduce in module 3, when you talk about deep state-based models, we'll have more places where we will do it. So, so how do we actually characterize a Gaussian process? It is completely defined by its mean function and the covariance function. So what we saw with the multivariate Gaussian vector, we have multivariate Gaussian distribution. It was completely defined by the mean vector and the covariance matrix. And here, when we talk about Gaussian processes, the equivalent are the mean function and the covariance function. So there are many examples of covariance functions, and there's some of them are shown here. One is a linear function. So kappa is the value of the function computed at x and x prime. So the covariance function has two arguments. It has two values, x is one such vector. It can be taken at any instant in time, and x prime is at some other instant in time. And the way how you evaluate that particular covariance is using x transpose x if you want to assume linear covariance function. Now, one covariance function that is very, very popular is the squared exponential. And it has this form. So this squared exponential has also two what we call hyperparameters. One is sigma squared and the other one is L. Now, as before, you can assume that they are known, but you can also estimate them. So, and you estimate them from training data. So this squared exponential, like the other covariance functions, they measure what? They measure similarities between points. So when you have for the squared exponential x and x prime, you can clearly see how actually this squared exponentially measures the similarity between these two vectors. Machine learning is all about similarities. In our real life, we also do everything based on similarities. We recognize similar situations, and then based on previous experience, we act accordingly. So is the case with these methods. The Ornstein-Uhlenbeck covariance function has this form, as you see. So it is also often used in machine learning, but by far the most popular is the squared exponential. And the periodic is also often used depending on what kind of phenomena you use. For instance, in climate data, when you do climate data processing, there are lots of periodicities, and this is something that where one can use this covariance function. Obviously, in econometrics, you also have periodic behavior. So wherever you see periodicity, this is something you might want to consider to use. So here are some examples of Gaussian processes. So these would be examples of realizations drawn from the prior of a Gaussian process. So on the left are samples where the parameters are 1 and L equal to 2. And on the right, where sigma squared is 1 and L is equal to 10. Let me remind you what these are. So this is the sigma squared parameter here. And L is this parameter. So what you notice when you compare these two sets of realizations from the Gaussian process, the right one is much smoother, and the left one is more kind of local. What it means is that if you look at these, what that means is that these covariance functions measure similarities obviously in a different way, where for the left covariance function, you go further away from, say, let's say that you're looking at x and x prime. These are for the scalar cases. You're further away, then the similarity is dying very quickly. Whereas for the second one, when L is equal to 10, then this similarity still remains pretty high. So these are the kinds of things, again, that you can learn from training data. What type of parameters to use. It would really be decided by the data. So here is a heat map of the covariance functions from the previous slide. So on the left is what is here. This is the covariance function. So the left is these curves. And on the right are the curves where L was equal to 10. So you can now imagine that, so these are heat maps. You have this nice hill that shows how that measures the similarity between the points. So if you have, say, two variables, like in this case, x1 and x2, Then, of course, when along the diagonal, they're the same. So they're completely the same. And then as you get away from the diagonal, then it quickly dies off. So they're not much similar. Whereas with L equal to 10, then this similarity remains pretty high. So this is, again, a way to view the covariance functions with a heat map. And on this graph, we see the squared exponential for now the case when L is kept the same. L is equal to 2 in both cases. But what you change is this parameter sigma squared. This was this parameter sigma squared here. So sigma squared. And it's not surprising then when you see first when sigma squared is equal to 1, you get the curves, the realizations on the left. And when sigma squared is equal to 2, you get the very smooth curves on the right. And this is how they look, how the heat maps look in this case. So there are actually two ways how you can control the covariance, the similarity. One way is through L, the other one is through this parameter sigma squared. So the larger values of sigma squared increase the covariance between the variables. So now let us take a look how we use this for what we will need. So just reiterate that once we sample from the Gaussian process, we have to deal with multivariate Gaussian PDS. And what we will do is we will actually, yes.
Would there not be identifiability issues when trying to learn L and sigma squared, because they literally do the exact same thing. One's just a factor of the other. If could we just go back to the slide where we actually have the models defined, or covariance is defined rather? Yeah. So sigma squared and 2L that like one can just factor out the 2L squared into a term just out from the expression. And
so
if I'm not messing anything up here,
right. So in this question about identifiability often arises in many fields, in particular in control theory, and obviously, but in our context, when at least the way how I see it in Bayesian theory, you have in this case two unknowns, sigma squared and L, and then you have a prior for these. And then what you do is you try to get the posterior of both parameters. So for our purposes, we don't really even see, so if you say that you can have two different values of sigma squared and L, or rather two, let's see what is a good way to explain. So what we want is the posterior of these. And now if you actually look for point estimate, you may get a bunch of values that will have the same value of the posterior. But I don't think I would not be worried about this at all, for as long as we use these values for the purpose of learning the function. So yes, it could happen that you can have an identifiability problem. There is actually later on there will be another place where we will have identifiability issues, and there is a way how to go about that. So to come back to what your question is, there may be cases where you could have a point estimates which will be the same value of the posterior.
okay. So the reason I was just assuming naively point estimates all the time, but
I could not hear. Can you repeat?
I work in a point estimate world a lot of the time, so it makes sense. I was keying on that. Okay, but if we assume the posterior on them, then the identifiability are much.
Yes.
Okay, thank you very much.
Another way for people who don't like Bayesian theory, they use what is called regularization. So they find ways to get around this, but this is just a gimmick. Right. So what I said was, and this is something that will happen when we implement Gaussian processes, is that you will have samples of the function. So what I mean by this is the following. So you have an unknown function. So let us say y equals f of x plus some perturbation. Then what I have, you have samples, you observe some x. This is your input. And then for that input, you observe the output y. So you have x and y. So this is one observation. This could be what is known here. Let us say that there is no noise for now. This is your f1. Then you have another value of x and another value of y. This is now x2, y2. This is your f2. And you can have such n observations of the function, f1, f2, and fn. So now remember, we said that f is modeled. These samples are modeled to come from a Gaussian process. What this now means is f1, f2, all the way to fn, they have a multivariate Gaussian distribution. So let me repeat. So we have samples of the function, and we call them f1, f2, fn, and these samples have multivariate distribution, and let this distribution has mean mu and covariance matrix sigma. So now I go back to what is given now at the bottom of the slide. So this function f is considered to have a prior that is coming from the Gaussian process, and f of x has mean m of x and covariance function kappa k x prime. So suppose that what we model is y, which we observe, and then y is a function of x through f of x, and then this f of x is perturbed by some noise. X is observed. This is the input to the function, and then epsilon in this case is standard Gaussian, and but the noise variance is sigma epsilon squared. So f of x is unknown, and we use the GP prior for f of x, and it is given by this equation, p of f of x given theta. So theta are some parameters like sigma squared or L that I mentioned that are part of the kernel of the part of the covariance function of the Gaussian process, like in this case that you see at the bottom. So sigma squared and L. So we have f of x, which is unknown to us. F of x is coming from a Gaussian process with some covariance function that we choose, and then we write this as given by the second equation. So let us go back and recall what we wrote about the Gaussian, multivariate Gaussian. So if we have two vectors, y1 and yt, we can stack them into one y. And then the mean is mu and the covariance is c, where the mean is, again, split into the mean of the first vector, y1, and the mean of the second vector, y2, so mu1 and mu2. And similarly, for the covariance matrix, we have in block matrix representation, C1 and C2 are the covariances of Y1 and Y2, and A is the matrix that represents the cross covariances between Y1 and Y2. Then what is important is this Y1 vector, when you look for the marginal distribution, will simply have a mean mu1 and covariance C1. Similarly for the vector Y2. So then the other thing that is important to remember is that when we want to write the conditional density of the vector y2 given the vector y1, then what we end up with is another Gaussian is given with a conditional mean and conditional covariance matrix. And these are given by the last two equations, the conditional mean and the conditional covariance. So why I am coming back to this, I'll explain in a moment. What we will have actually is with the Gaussian process machinery. What we will have is all the time implementation of what you see here. So how to obtain, say, y2 given y1, and how to update then the function that you're estimating given the data that were observed up to a certain point, then by adding a new.
Module 1 again.
This is module 1. Right. So to summarize again, what I wanted to say with this slide is that when we want to do predictions, when we want to predict y2 given y1, then we again get Gaussians, which whose means and covariances can readily be obtained. So one thing that I want you to pay attention to that will come up very important for us is this operation of updating mu and updating C. What is critical here is one very expensive operation, and that is the inversion of this covariance matrix. What will happen, and I'll repeat it again later, is that when you do training of your model, when I say training, when you're trying to learn the function, then you have to invert this matrix C. And the size of the matrix is equal to the number of data that you observe, number of input-output data. Input, how many X's, how many Y's you observe. Now, those of you, many of you follow also what's happening with in the deep neural network world. There, the assumption is that you have enough data to learn because there's so many unknowns to be learned. Gaussian processes are kind of the opposite. We don't want many data because we have problems with this these inversions. At some point, if you have, say, 1 million data points, you have to invert 1 million by 1 million matrix. And that's not pleasant. So, but fortunately, there are ways, and I will talk about one way of how to handle this problem of inverting these, how to avoid actually inverting these high-dimensional matrices. So again, here the nice thing is that we still work with Gaussians, and this is what makes, to a large extent, the application of Gaussian processes for estimating functions very attractive. So now I also said that we have these Kaggle parameters, and in this case, it's sigma squared and L squared. The parameter L controls the horizontal length scale of the data, and the parameter sigma squared, the vertical scale of the data. One thing that I wanted to also mention is, and something that was mentioned earlier today. So one place where you want to estimate these parameters L and sigma squared is from the evidence function. So integrate out everything you can, but you keep the keep L and sigma squared. You keep them as constants, and then you get the likelihood function after marginalization of all the other unknowns, and then you find the maximum likelihood of these parameters. This is how it is typically done. So these parameters can be or are typically estimated using marginalizations, using the evidence function. Now, what is also interesting is you can do kind of also beautiful things with Monte Carlo sampling. So you can find, if you want, the posterior of these parameters if you find that to be useful information for you. So this is also possible. So here is what I meant. So the maximum likelihood estimates of L and sigma squared are obtained by using the evidence. So P of Y is the evidence, but evidence conditioned on the hyperparameters. So just to make it faster, you run a gradient optimizer to estimate L and sigma squared for this particular example. Now, here is one other thing that I would also like to spend a minute or two on. So you can write your covariance matrix as is given on the screen. So what is different here is the following. Every dimension, so X is a vector. This is the input vector. So this input vector is a vector. So remember, in our case, it'll be elements of the state process. X1, X2, X3, X4, X dx here. So what you're doing with this particular covariance matrix, you are giving each of these elements the possibility of different weights, different importance to basically to your model. So in machine learning, this would mean X1, X2, X dx would be different features of say, a particular patient in medicine. And then with these parameters L1, L2, L dx, you give different importance to the features to what you want to predict. If you want to classify or if you want to do regression. So this is a mechanism to give importance to the different input features. And there is a way how, in fact, one can use these to what is known in machine learning automated relevance determination. So you determine automatically which features are important, which are not. So is the case here because if we want to use it in the context of latent processes, then each of these elements of the latent process make a different importance in your model. And they are estimated in the same way as these other hyperparameters using the evidence function. So here is an example of a Gaussian process used to learn a function that is completely unknown. So the function is given by x squared sine x. So it is unknown to us. What is known are these red points. The red points are noise points on the left with less noise, on the right with more noise. And you can see that the function, which is here plotted in dashed red, the Gaussian process estimates it in the following way. So for every point, let us pick a point here from this, point 6, for instance. So you can see for 6, this is the mean of the prediction. Oops. This is the mean of the prediction. So the green curve represents the mean of your prediction. And the gray area represents the area of uncertainty. So, and it is a 95% prediction interval. So one nice feature of Gaussian processes is that they provide probabilistic results. Everything is given by probability distribution. So not only that, but in this particular case, the estimate is a PDF for every x. So you can imagine here for this particular time instant, you have a Gaussian that is centered at that green line. So on the left, we don't have much uncertainty because this is a very well observed, almost noiseless data, but on the right, it is with lots of noise. So here is the slide that now addresses this problem of computational bottleneck. And the bottleneck is this inversion of the covariance matrix from the training data. So here is the equation that we will use to predict y2 given y1. So for example, when we deal with Gaussian processes, we deal with very similar equations, and the problem is this C1 inverse, as I mentioned earlier, in both the equation for the mean and the equation for the covariance. And the computational complexity is of the order of dy cubed. So in this case, it is just the prediction of y2 given y1, and then what you use here is a covariance matrix of y1, and if y1 is of dimension dy1 and dy1 is very large, then this is computationally challenging. So one approach, you can ask, so how do we deal with this problem? One approach of dealing with this problem is to use representative points. What is meant by representative points is the following. So let us say that you have a cloud of points, let's say 1 million points. So rather than trying now to invert a matrix that is 1 million by 1 million, you try to find representative points which will represent this cloud very well. And you can choose maybe 1,000 of them. And then from then on, you use these representative points to conduct your prediction or your classification. And these points in the literature are known as inducing points. So you have representative points, and then you can also optimize where to pick these points. And this is one way of doing it. But this is not the way that we'll pursue here. So as I said, there are several ways how you can kind of sparsify your Gaussian process and then use approximations so that you can work with lots of data. So instead, what we will do is we will work with what is known random feature-based Gaussian processes. So what we have is, first of all, we work with what is known, I'm sure you remember from your classes, I don't know if you have had classes on statistical signal processing, for instance, where one spends lots of time to talk about power spectral densities. So power spectral densities are defined for stationary, white-sense stationary processes. So if the Gaussian process is white-sense stationary, it has a power spectral density. So let this power spectral density be S omega here. And then obviously it has the inverse Fourier transform of this power spectral density will give you the covariance function of the process, which is kx minus x prime. So this is a shift invariant because it's white-sense stationary. And then what is interesting is the following. You can sample frequencies from P of omega. P of omega is a probability density function that is proportional to the power spectral density right here. So P of omega is probability density function that basically has the same shape as the power spectral density. So the power spectral density, we can find the power spectral density, for instance, of your favorite kernel, your favorite covariance function. And you can sample frequencies from that PDF. So then what you can do is if you have samples from this PDF, P of omega, then you can approximate this operation, the one that we had here, of using Monte Carlo samples, like this. Here sigma 0 squared is the value of the covariance function at 0. Now, Since S of omega, the power spectral density, is a symmetric function, then it makes sense to sample frequencies omega j minus omega j. And the reason for this is you want to make sure that your kernel will be real. And then one can also use this identity, cosine omega transposed, x minus x transposed, where you have cosine x transposed omega, cosine x prime transposed omega, plus sine x transposed omega, sine x prime transposed omega. What this leads us to is the following. And this is something that will give us a lot of room for very nice applications of Gaussian processing, is to construct random features. To construct random features that we will use later for our deep state-based models. Let me explain. So what you see here, the first identity shows a random feature obtained from the samples of the power spectral density that corresponds to a particular kernel. So you sample j times, capital J times, and then you construct your feature phi of x. X is your input by constructing this vector. So we have again j such samples. So first, let me tell you this: x is your input. X is dx dimensional. So when you sample dx dimensional, dx frequencies from the power spectral density. So this is your omega 1. And then you'll sample again. This is your omega 2 and omega j at the end. So the vector omega is, of course, has to be the same size as the size of your input vector x. So then the kernel function kx prime, the one that we started with, is approximated by this dot product phi x transpose phi x prime. And then this is the key. This function f of x, the one that we don't know, we are modeling using this product phi x transpose theta, where theta are parameters of the approximating model. So now here's what we did. We started with a kernel. We created for that particular x, we created a feature vector phi x. And now we are multiplying this phi x transposed with theta. So basically, we obtained, theta is not known, and something that we will learn from training data. But theta is now linear. Theta is now linear. Unlike the original Gaussian process with, say, radial basis function, these squared basis functions, things were nonlinear. Here now we have a model of the Gaussian process where the features are given by this first equation. And then these features multiply a static vector theta. For now, we can even change it later to time varying, but for now it is static, it doesn't change. So now imagine you have a bunch of inputs, outputs, and from these input outputs, you can readily estimate your theta. It's linear vector. Vector that appears linearly in the model. And then using these estimates, you can predict readily the next value of y if you are given a new x, a test x. So I will repeat again. You are given a way how you convert your original into a set of features for every x that is given to you for training. So x has particular y, another x, another y, another x, another y. For each of these x's, you construct a feature, phi of x, phi of x1, phi of x2, phi of x3, and so on, phi of x capital N. You observe y1, y2, y3, yn, and for so they're connected through this equation that I show here. So let me find this equation here. Yeah. So this phi of x that you see now on the top is your phi of x times theta transpose times theta. So obviously, to estimate theta, you can still estimate it with one sample if you have a priori distribution for theta. But with more data, you'll get a better and better estimate of theta. So the idea again is to linearize the problem. And with the linear problem, life will be much easier. Now, what is important to note is that the model is very nonlinear in the input features, in the input x. In our case, x will be the latent process. So the output will be a very nonlinear function of the input of the latent process. So this is something that we will keep using in the last module. So let me summarize with the following. So why are Gaussian processes attractive as a machine learning method? So I listed here two big advantages. They provide well-calibrated predictive uncertainties. As you well know, all these non-Bayesian methods suffer a lot, and a big move today still in machine learning is to study uncertainties. And all these methods like deep neural networks have difficulties in quantifying uncertainties. And what is also important is they can work with small number of data. In fact, they prefer smaller number of data. And then what I discussed at the end about the random feature-based Gaussian processes, they have the additional advantage that the unknowns are now linear parameters. And that is something that we will exploit in the last module. So stop here, I think.
We have 30 minutes.
Break, and then I'll